morning. I'm the representative from Shatin College. Our registration number is 90010, and our title is Erdos-Szekeres conjecture. Erdos and Szekeres in 1935 have proved that there exists a smallest number, Gn, in general position on a plane containing at least one convex angle. General position means no three points are collinear. And they also conjecture that for any integer greater than or equal to 3, Gn is equal to 2 to the power n minus 2 plus 1. In our study, we cope with this problem using another function, fn, defined as follows. The largest number of points which are in general position on the plane containing no convex angle. And consequently, fn is equal to Gn minus 1. And the conjecture will become fn is equal to 2 to the power n minus 2. And then let's just start with the trivial cases when n is 3. Any 3 point must guarantee a convex triangle. Therefore, f3 is equal to 2. That is trivial. And then let's just consider the case n is equal to 4. We start with a triangle with a point in it. And when we add one point, it will become the figure on the right. And you can always find a convex quadrilateral. Therefore, f4 is equal to 4. And then we try to do some more experiment in order to find the value of f5. In the screen, you can see a convex quadrilateral below. And when we add one point to the shaded area, there will definitely a convex pentagon. So we always want to eliminate these shaded zones. And when we eliminate all the zones on the plane, that means the value of f5 is found. And then, as you can see, we try to start with a convex quadrilateral, and we add one point, one by one. And we finish hundreds of them. And we foresee that we have several hundreds more to do. But we start with another way, because this is very difficult to finish all them. And then now we introduce the way we describing the zones. And on the left, you can see the segment, rays, and line. And that is very simple. And the right, you can see definition of beam. The area bounded by ray EA, ray CB, and segment AB are called beam CE and AB. And in this way, we can categorize zones easily. And then we describe some way to describe a point set on the plane. In any point set, there must contain a convex polygon that will always envelop the remaining points of the point set. And here is an example of 6-4. You can see a convex hexagon is enveloping the remaining 4 points. Therefore, the configuration of this point set is 6-4. And then it's proved by former mathematicians that f5 is equal to 8. Therefore, we start to list all the possible configuration of x points. As you can see, there are 4 cases: 4, 3, 1, 4, 4, 3, 3, 2, and 3, 4, 1. Let's just consider 4, 3, 1, and 3, 3, 2. As stated by our paper, lemma 1 and lemma 2, these 2 cases are rejected. Therefore, any 8 point of these 2 configurations must contain a convex pentagon. And then how about 4, 4, and 3, 4, 1? Actually, we are happy that we found 2 examples, while on the left are found in the previous paper, 4, 4 configuration. And on the right, you can see example of 3, 4, 1 configuration that does not contain any convex pentagon. And the figure in the right is created by us. And then we are one more step from proving f5 is equal to 8. We have to add one more point to show that any 9 point must contain a convex pentagon. And then when we add one point to these 2 configurations, 3, 4, 1 and 4, 4, we will get these 6 configurations. While the red one is rejected by lemma 1, and the blue one is rejected by lemma 2. And you can see the green one, there is always a number 5. Therefore, we can find a convex pentagon. Therefore, we summarize all these findings, and we can simply say that f5 is equal to 8. Through this step, we can show that the conjecture is right for n is equal to 3, 4, and 5. But how about n is equal to 6? It is proved by former mathematicians by computer programs that f6 is equal to 16. But we don't think this kind of proof is elegant, because this is done by computers, and we do not find any examples of a point set of 16 points graphically in history. Therefore, we try to find a graphical solution to the F6, and we try to list all the configuration as we have done before to F5. As you can see on the screen, there are so many cases that's stated in the paper. There are 70 cases more, and we don't want to do this. Perhaps you may do it for us. And then on the screen, you can see two examples of F4. That is on the left and on the right. When we combine these two examples, we may somehow get F5. But, the previous page. And then we try to think if we can put two examples of F5 to get F6. That is the configuration of 4444. But sadly, we failed. And then we turn on to another way to rotate 3 regular pentagons. And amazingly, we found a result. An example of 5551 without forming any convex hexagon. And luckily, it is also similar to our regional flag of Hong Kong. And then we think, how do we prove these examples? By exhaustion? Definitely not. Because 16C6 is 8008. Perhaps we can just finish it before Jesus comes back. And then we try to have study on the structure, the special structure of this 5551. We can always find out the situation here stated on the screen. Therefore, we try to have more study on these situations. And then we introduce theorem 3. There are 2 points in that beam, that is the triangle. If the line formed by these 2 points doesn't cut the segment, we can have an n+2 gon and further facades. And we now show some simple examples. On the left, you can see originally there are 5 points. And the 2 points, the line formed by that 2 points doesn't cut the segment. Therefore, we have a convex heptagon. But on the right, the line is cutting the segment. Therefore, we have only a convex hexagon. And then we introduce another lemma that is useful to prove our F6. The lemma states that any configuration 5-2, if the line formed by the 2 points in that pentagon doesn't cut the adjacent side of the pentagon, there won't be a convex hexagon. And then simply, by lemma 4 and our findings, we come with lemma 5. It states that any point set of configuration 5-3, if the line formed by that 3 point doesn't cut the same opposite side of the pentagon, there won't be a convex hexagon. And then using theorem 3, lemma 4, lemma 5, we can simply prove our examples by cutting our example into 2 parts, upper part and lower part. We want to find out more situations stated in that theorem 3 and lemma 4 and 5 in order to prove there is no convex hexagon. And luckily, we have come up with the result that the lower bound of F6 is equal to 16. And then for completeness, we want to show that if we add 1 point to the examples, there will be a convex hexagon. But dividing the 5551 point set into 4 parts, as you can see, the shaded area, 4 cases, and we'll add 1 point to that. And the result is that if we add 1 point to any of this area, there will be a convex hexagon. And then that's all we have been doing for last year. And after we submit our paper, we didn't stop. But instead, we try to find if there is a point set of 4444 configuration forming no convex hexagon. Luckily, we success. With this example, you can see 4444, and there's no convex hexagon. And it is proved by our teammates. We strongly believe that if we put 2 copies of Fn, we may somehow get Fn+1. And if this is true, the equation is correct, and it can be proved, and consequently, we can find that Fn is equal to 2 to the power n-2. Or in other words, the conjecture is correct. And that's all we have done. Thank you for your attention.